Good morning. Welcome to our final day of notes in Module 6, Lesson 2 on ionic bonds and ionic compounds. There's no need to fill out a new header since these are a continuation of the Cornell notes that we were taking yesterday and last Friday. You may want to put a date in the margin. Today's date is 2/7/2023. Yesterday, if you remember, we were talking about the crystal lattice and electrolytes. And today we're going to talk about lattice energy, that fifth term in the column. I'm just going to slide through the notes here and get to where we were yesterday. Yesterday we were talking about properties of ionic compounds, and we found out that they have high melting points, high boiling points. They're solids at room temperature, and they're also electrolytes when dissolved in water. And if you don't remember what that is, electrolytes, that means that the charged particles in the ionic compound, they separate when dissolved in water, and then that will allow water to conduct electricity. So let's practice quickly. Remember, you can pause the video if you need to. You can work this out and then come back and play the video again to check your answer. But what I'd like you to do is use electron dot structures to show the bonding between aluminum and oxygen. And so I'm going to go ahead and do that up here on the board. We've got aluminum, and aluminum with 3 dots, 3 valence electrons, plus oxygen with its 6 valence electrons. And aluminum, if we take a look, can only give 2 away to this oxygen. So what we do is we add another oxygen with its 6 dots. And this dot can go right here, that valence electron. But the oxygen still needs 1 valence electron to be stable. So we will add another aluminum. And we'll take one of this aluminum's valence electrons and put it on this oxygen. That oxygen is now full. So we're going to do 1 more oxygen. And that's where these last 2 valence electrons will go. Okay, then we have to draw the finished product. And we're going to end up with 2 aluminum ions. Each aluminum ion gave away 3 electrons, so those aluminum ions will have a +3 charge. It doesn't really matter whether that +3 goes in or outside of the brackets. Okay, plus we're going to have 3 of the oxide ions. Remember, they have their 8 dots, so you have to put the 8 dots around it. And those 3 are each going to have a -2 charge. And then remember, they're doing this to release energy. So at the end of the reaction, they're going to be stable. And the reason they're stable is because they release energy. We also want to look at the charges. 2 times +3 gives us a +6 on this side. 3 times -2 gives us a -6. So the charges are going to balance out at 0. And our formula, there are 2 of the positive cations. So it's going to be Al2. And then 3 of the oxide ion. Al2O3 is our formula. And then what I'd like to do is I'd like to quickly show you what the crystal lattice looks like for aluminum oxide. Aluminum oxide is going to have a crystal lattice where the positives and negatives will space out so that it minimizes repulsion. And there's attraction between each ion. If you remember from yesterday, the crystal lattice is that repeating pattern of positives and negatives that we'll see in ionic compounds, in ionic crystals. So I'm going to start off with an aluminum. And the aluminum, if we remember, has a 3+ charge. And around it, I'm going to put an oxygen. So here I'm going to do an oxygen with my 8 dots. That's going to be right next to it with the -2 charge. Then I am going to do another aluminum right over here. Okay, remember, we want to alternate positive and negatives, okay? Then I'm going to do another oxygen. That with its -2 charge. And if you look here, the positives, I've got +6. The negatives, I've only got -4, okay? So I need to add another oxygen someplace. I'm going to come over to this side and add my oxygen. And again, that's a -2. Now the charges balance out at 0, and I've got Al2. Here's my 2 Als. And then O3 Here are my 3 O's. Okay? And that balances us out. But remember from yesterday that this would be too small for us to see. We need to repeat this pattern, about 10,000, maybe more times in order to get a crystal large enough for the human eye to see. So I'm going to continue my crystal lattice, and all I have to remember is that you have to kind of space out the positives and negatives. So I'm going to put an oxygen, an oxide ion, down here with its -2 charge, okay? Then I'm going to put an aluminum here. And remember, now these aluminums and oxygens, they're next to oppositely charged ions. That's the way we want to spread out this crystal lattice. This has a +3. Okay, over here, I'm going to do another Al, okay? And that's going to be a +3. Okay, I'm going to do an oxygen over here. And here I'm going to do a -2. If I look now at what I've drawn, you guys, I'm going to just quickly add up all my negatives in the entire picture. So I've got 1, 2, 3, 4, 5 negatives. That looks like I've got a -10. My aluminums, I've got 3, 6, 9. I've got a +12. I have to get these charges at 0, so it looks like I have to add another oxygen. So I'm going to add another oxygen out over here. And remember, that's the -2. So you guys, I would repeat this pattern, alternating positives and negatives, until I got big enough to see an ionic crystal. And you guys, that is why we call this formation the crystal lattice. Remember, it's a repeating geometric pattern of negative and positive ions, okay, that gives us our different properties for ionic compounds. I'm going to erase this. Okay, some things I want to talk about quickly are the physical properties of ionic compounds. They're controlled by the strength of the crystal lattice. So these physical properties, like melting point, boiling point, and hardness, they're controlled by how strongly those ions are attracted to one another. And we also need to remember that ionic bonds, they are strong bonds due to the attraction between the positive and negative. But again, these properties, like boiling point, melting point, and hardness, they're controlled by the strength of the attraction. The greater the attraction, the greater the melting point, the greater the boiling point, and the harder these compounds are going to be. Okay, I'm going to move on to my next slide. So we have this thing called lattice energy. Remember, you can pause the video if you need to write down definitions, but I'm going to continue to talk. Lattice energy is the energy required to separate 1 mole of ions in an ionic compound. So what lattice energy actually is it's the amount of energy you need to separate those little positive and negative charges. It's going to take energy to pull that attraction apart, and that's what lattice energy is. And the greater the lattice energy, that means the stronger the ionic bond. The stronger those things are held together. So things like melting point and boiling point and hardness are kind of controlled by the strength of that lattice energy. I see that I missed a G on melting point here. I'm going to add that. Okay, so again, the greater the strength of attraction, the stronger the lattice energy, and the stronger the ionic bond. Okay? Look at the door. So if you've got higher melting point, higher boiling point, harder solids, you have a stronger ionic bond, you've got greater lattice energy. Okay, so the last thing I want to talk about is how we know whether or not there's a stronger ionic bond. And that depends upon the lattice energy. So lattice energy depends upon 2 things. It depends upon ion size, and it depends upon the charge of the ions. Okay? So smaller ions, you guys, are going to have a greater attraction, so they're going to have a greater lattice energy. If you think about smaller ions, there's going to be less distance between the nucleus of one atom with its positive charge attracting the negative electrons of the next atom. So they're going to have greater lattice energy. There's a stronger attraction. It's harder to pull them apart. And then the other thing we need to look at, you guys, let me get this erased. The other thing we have to look at is ions with greater charge have greater attraction or greater lattice energy. So if you've got a +3 and a -2, that's going to have a greater attraction than a +1 and a -1. Hopefully that makes sense. Okay, here's an example here of some compounds with different lattice energies. I just want to look at 3 of them right now. I want to look at these bottom 3. They're all compounds with sodium, and then the second element, you guys, is a halogen. And if we look on our periodic tables, we know that halogens get bigger as you go down a group because you're adding more energy levels. So if I look at sodium iodide, sodium bromide, and sodium chloride, the largest one would be sodium iodide. That has the least amount of attraction, the lowest energy. You guys, the smallest one out of those 3 would be sodium chloride, and it has the greatest amount of lattice energy. And the reason is because chlorine is a smaller ion than bromine or iodine. Chlorine is smaller. Smaller ions have greater attraction, thus greater lattice energy. Okay? If we look over at the right-hand side of this chart, just going to take a quick look. We've got these 2 that have extremely high lattice energies. We've got a 2,000 and almost a 4,000. Why are those lattice energies? Why is the strength of attraction so much greater? It's because of the charges holding those ions together. If you look at all of these other ions, they're all elements from group 1 and group 17. If we look at these 2, there's a difference. Strontium is from group 2. It's got a 2+ charge. Magnesium is from group 2. It's got a 2+ charge. You guys, there's greater attraction. If there's greater charges, there's greater attraction. Chlorine here has a -1. Oxygen has a -2. That's why this is so much higher. But these 2 have greater lattice energies because that force of attraction, a 2+, trying to attract a 1- or a -2, is much greater than all of these 1+ and -1s. All right, that's it for the notes. Before we go, let's just take a look at 2 examples. And the 2 examples I want to look at are these 2. So it says in each pair, which has the greater lattice energy and why. So if we look first at MgS or MgI2, okay, you guys, it has nothing to do with the fact that strontium and iodine are in different areas of the periodic table. It has to do with the strength of attraction, the charges. You guys, magnesium has a 2+ charge. Sulfur has a 2-, okay? Magnesium a 2+, iodine's only a 1-. So you guys, the greater lattice energy would be the MgS, the magnesium sulfide, because the strength of attraction of those charges is so much greater. You guys, down here, the charges are the same, +1, +1, -1, -1, okay? So now we have to look at where those ions are on the periodic table. They both have the chloride ion, so now we have to look at sodium and potassium. Whichever one of those is smaller is going to have the greater lattice energy, the greatest force of attraction. So you guys, sodium is up higher than potassium in that group 1, the alkali metals. So sodium chloride is actually going to have the greater attraction. That's it for the notes for today. Hopefully that made some sense. Come see me if you need some help. And hopefully I will see you tomorrow.